Hello and namaste everyone. Welcome to lecture 46 of this NPTEL course on stochastic approximation. In this week we have been trying to see how we can make use of stochastic approximation principles to understand the behavior of the Q-learning algorithm. In particular, we were interested in seeing if the Q-learning algorithm can be used to find the optimal policy, right. And in the previous class we have discussed the Q-learning algorithm's update rule. Then we have shown that its iterates are almost surely bounded. Furthermore, we have shown that its limiting ODE solution trajectory exists and are unique, right. And we also introduced this notion of this vector comparison lemma and the switch system theory, which tells us if you have a arbitrary switch system, what is a sufficient condition that guarantees that all its solution trajectories almost I shouldn't say almost surely because the limiting ODE is deterministic, right. What is the sufficient condition under which the origin is globally asymptotically stable. So we discussed some condition that ensures that, and now what we are going to do is we are going to see how such a condition and also the vector comparison lemma can be used to say something about the behavior of the solution trajectories of the limiting ODE associated with the Q-learning algorithm itself. So with this background in mind, let us begin our formal discussion, right. So our goal is to look at the asymptotic behavior of the Q-learning algorithm. So recall that the Q-learning algorithm has the update rule that is given over here, that is Qn plus 1 equals Qn times Qn plus alpha n times delta n times E of Sn an, right, where delta n is the TD error that is mentioned over here. And last time we saw that the limiting ODE associated with this algorithm is given in the following way. It is Q dot of V equals D subscript nu, where nu is your behavior policy, times R plus gamma P capital Pi subscript pi Q times Q. So this operation basically picks for every state S the action that maximizes your QSA value minus Q. So this was the limiting ODE that is associated with this algorithm, right. And in the last few minutes of the previous class we showed that this function over here is Lipschitz continuous in Q, and hence its solution exists and is unique. So our goal today is to ask, if the solution exists, can we somehow guarantee that the solution will actually converge to Q star. Is this okay? So then what we did was we want to make use of the switch systems theory, and for the switch system we have to somehow make the origin the equilibrium point, and hence we looked at this shifted trajectory. In particular we looked at x of t equals q of t minus q star, and then we showed that x dot of t satisfies this equation where this q is basically x of t plus q star, right. And we wanted to see first of all because the solution existence and uniqueness of solution for the q dot t equals this ODE is guaranteed, one can conclude that this ODE also is well posed, in that for any initial point one can guarantee the existence and uniqueness of solution. And now what we will do is we will make use of this vector comparison principle and switch system theory to say something about the limiting behavior of the solution trajectories of this ODE, right. And as I said, this ODE is slightly challenging, right, and we want to somehow make use of this vector comparison lemma to come up with a simpler ODE that is easy to analyze, right. So towards that what we are going to do is we are going to define f to be this function. So f of x is basically whatever you have here, gamma p, and wherever there is this little pi k I am going to replace it with q x plus q star, and this identity is as it is, right. And similarly this expression is now replaced by gamma d nu times p capital Pi subscript pi of x plus q star minus pi of pi q star, what we have over here, times q star, right. And now what we are going to do is, this is f of x. Now similarly define f bar of x, where you drop this latter term and make use of only this expression. So basically your f bar of x is d nu times gamma p capital Pi subscript pi x plus q star, which is what you have over here, minus this expression, right. Now one can ask, why are we looking at this expression? You will soon see. The idea is that this expression is simpler to work with, and somehow we will use this switch system theory to understand the dynamical system which is governed by this f bar driving function. Okay, let us see how we can do that. So the first claim is that for any x, your f of x is upper bounded by f bar x, right. So first keep in mind that your f and f bar, they take in as input a vector and spit out a vector. So when I say this inequality holds, what I mean is that coordinate wise the output of f of x and the output of coordinate wise f of x is less than equal to f bar x. That is what I wanted to say, right. And why does this follow? It follows because in the definition of f of x you have this additional term. So let us focus on this expression, okay, which is what I have written over here, and let us try to understand what is happening. So if I multiply pi subscript pi q star with q star, so this will be the sth coordinate will basically be max of q star SA with the max taken over A. This is what will be the sth coordinate. Now similarly, what will be this times this? Now notice that here the greedy action is taken with respect to this value. In other words, if I look at the sth coordinate of this expression, it will be q star of S, right, and instead of now being the action that maximizes q star, it will be some A, let us call it as bar of S, where A bar of S is basically the argmax of okay, let me just see if I can move this to the left so that I have some space. So where your A bar of S is basically the argmax over A of x of SA plus q star of SA. Okay, so you basically look at this vector for different values of SA, pick the action which maximizes this and use this action over here to get q star S A bar S. That is what the definition of this matrix times q star implies. In particular, this quantity over here dictates which action we will be selecting, right, and since this quantity leads to the max of q star SA and whatever we have here will be less than the max. So one can easily see that this expression minus this expression will be less than equal to 0, from which we can conclude that f of x is upper bounded by f bar x, right. And since the coordinates of this expression, so notice that you are multiplying this quantity with gamma d nu p, right, and all coordinates of this matrix are non-negative, one can show that indeed this conclusion holds. Is this okay? So let me again repeat what we have done. We first show that this expression, right, is a vector whose all entries are non-negative, right, and since I am multiplying this sorry, I should be careful. I want to say that the entries of this vector are non-positive, in other words they are less than equal to 0, and since I am multiplying it with a matrix made up of non-negative entries, the every coordinate of this vector will be less than equal to 0. One can easily see that, and from this fact one can see that f of x is less than f bar of x. Is this okay? So now what we are going to do is we are going to look at the ODE which is driven by f bar of x, and let us see what we can say, right. So so you have this x dot of t equals f bar of x, right, and in f bar of x you do not have the second term. So notice that there is nothing like this. So now for every x, so you will think of your sigma of x basically being dictated by where x is. So if your current x is x, right, or x of t is x, then the driving matrix will be A subscript x, which is given over here, right. And if you remember the switch systems result that I had spoken about in the previous lecture, right, in order to show that the origin of the switch systems ODE, right, is globally asymptotically stable, we need to show that there exists a matrix L, and some complementary matrices A bar sigma, in this case it will be A bar x, such that LAX equals AX bar L, and this A bar x, right, needs to be having this negative diagonal dominating condition. So here what we will show is that this AX matrix itself has this diagonal dominating condition, and hence we can work with L, which is equal to the identity matrix. In other words, we will show that this A subscript x, whatever be your x, okay, which is basically the sub matrix is decided by this quantity over here, right, this matrix has a negative diagonal dominating condition, and hence so I should actually be careful, this is without x, okay. So the matrix is actually this, and then you multiply x with this matrix. So we want to show that this matrix over here has a negative diagonal dominating condition, right, and hence one can use that switch system ODE theory to conclude that the origin is a globally asymptotically stable equilibrium for the ODE x dot of t equals f upper bar x. So to show that this A subscript x has a negative diagonal dominating condition, what we will do is we will pick the ith diagonal entry of this, and then we will look at the sum of absolute values of the off diagonal entries, right. So the ith diagonal entry of this matrix is basically the ith diagonal entry of this, and the ith diagonal entry is basically the ith diagonal entry of dv, right, and since this is a diagonal matrix, right, so one can show that the ith diagonal entry of this matrix is basically the ith diagonal entry of dv times the ith diagonal entry of this matrix over here, right, and similarly the ith off diagonal or the ijth off diagonal entry of this matrix is basically dvi times the ijth entry of this matrix over here, right, and since the ith diagonal entry of I is 1 and the ijth off diagonal entry of I is 0, right, one can drop this I from this expression and write it in the following way, and since the ith diagonal entry of this identity matrix is 1, one can see that this expression can be written in the following way, right, and since all these so just 1 minute. Okay, so what we will do is, so I have actually written, one needs to be careful here, okay, so I have written this upper bound over here, but I am just checking why is this guaranteed to be positive here. So let me just make sure. Okay, so I have to be careful here. So what we will do is we will take this ith diagonal entry outside, okay, with an equality here, okay, and I will write this as dvii and multiply it with this expression, right. So I will have the ith diagonal entry of ii and multiply with this expression, right, and one can then see so forget the inequality, I am working with equality, so I am basically taking this expression outside in common and then looking at what we have over here, right. So now let us see what is happening here. Here you have gamma, here also you have gamma, right, and then one can see that this expression is basically gamma times p pi x, the ith diagonal entry of this, right, plus the absolute value of this thing, but because these expressions are all non-negative, one can drop the absolute value and one can hence get the expression without the absolute value, and this will be j not equals I, the ijth entry of this quantity over here. So one can see that this matrix, your p pi x, actually is a row stochastic matrix, which means that its entries add up to 1, and hence one can see that this expression, which does not have any absolute values, actually adds up to 1, right, and because you are multiplying it with gamma, you will end up with gamma, right, and hence you will end up with gamma minus 1. Is this okay? And since this quantity is strictly less than 0, because we have presumed that the discount factor is strictly less than 1, hence this quantity is strictly less than 0, and hence if we multiply this with a non-negative quantity, that inequality continues to hold true. In particular, if we presume that the Markov chain induced by your behavior policy nu is ergodic, then this entries will be strictly positive, which using this one can show that if I multiply this with dVii, right, this inequality will continue to hold true, right. And since this inequality holds true, one can show that this AX matrix for any x has this negative diagonal dominating condition, and because it has this negative diagonal dominating condition, one can show that the origin is a globally asymptotically stable equilibrium for this ODE, right. So one can see that by working with this F upper bar, checking whether the origin is a globally asymptotically stable equilibrium or not becomes very easy. We just have to verify some algebraic expression. Furthermore, what we will now do is we will show that this F upper bar is actually quasi monotone increasing, whose definition I had described in the previous class. So if you have forgotten, you may either look up the definition from the previous class video, or you can go to that paper by Dongwon Lee and Niao He to check the definition of when do we say a function is quasi monotone increasing, right. So before we show that, let me just tell you why we are showing it, right. So here is the f of x update rule. So we have this ODE x dot of t equals f of x of t, and then there is another ODE where the driving function is f bar, right. So what we have shown is that all solution trajectories of the limiting ODE where the driving function is f bar actually goes to the origin. Now we would like to see if we can say something similar for the solution trajectories of the ODE where the driving function is f, and in order to be able to show that, we want to make use of the monotone the vector comparison principle, and for that we need that f be less than f bar, which we have already shown. Furthermore, we require that this f bar be quasi monotone increasing, and if we show that, then one can eventually claim that the solution trajectories of the ODE where the driving function is f is upper bounded by the solution trajectories of the ODE which is governed by the driving function f bar, right. And we know that all solution trajectories of f bar go to the origin, using which we can say something about the solution trajectories of the ODE which is governed by f, right. So let us try to show that. Our goal is to show f bar is quasi monotone increasing, right. And the way we will prove this is, we will consider an arbitrary input vector, let us say z, and another arbitrary vector p whose all coordinates are greater than equal to 0. So because all coordinates are greater than equal to 0, z plus p will be greater than equal to 0 on all coordinates, and furthermore let us presume that the ith coordinate of p is 0, so that the ith coordinate of z plus p, right, equals the ith coordinate of z, right. This is what I have written here. In order to show quasi monotone increasing, what we now need to show is that if I give z plus p as input to f bar and look at the ith output or ith coordinate of the output, that should be greater than the output when z is given as input, right. So let us formally state that, right. In order to show f bar is quasi monotone increasing, it suffices to show that EI transpose f bar z plus p is greater than EI transpose f bar z. So let us verify this, right, and notice that I only talk about I because this is what the quasi monotone increasing condition is. Only on those coordinates where z plus p and z are equal, I need to show that EI transpose f bar z plus p is greater than equal to EI transpose f bar z, right. So let us check what is the ith coordinate of this expression over here. The ith coordinate is basically EI transpose. So EI over here is the standard basis vector whose ith coordinate is 1, right. So EI transpose will when I multiply it with this, it will give me the ith coordinate. So EI transpose f bar z plus p, and now recalling what is the definition of f bar, it is basically gamma d nu, right, p times pi subscript pi, and since the input is z plus p, it will be pi z plus p minus d times z plus p, okay, or this d again should be d nu, right. So this EI transpose I can take it inside, and this will become EI transpose d nu p, right, pi subscript pi z plus p times z plus p, I am bringing it here, minus EI transpose d nu times z minus EI transpose dp. Is this okay? Now all coordinates of p are non-negative, right, and in particular the ith coordinate of p is 0 and d is a diagonal matrix, right. So since the ith coordinate of p is 0, one can see that EI transpose dp will actually be 0, hence this expression can be dropped, and one can then see that this whole thing equals what I have written over here, right. And now one can see that because your z plus p is non-negative, right, in fact I should claim that because your p is p is non-negative, one can see that max of ZSA plus PSA, the max over this quantity is actually bigger than the max of ZSA. So I inadvertently said that the Z is also non-negative. That is not true, right. It is your P is only non-negative, but one can see that because your P is non-negative, if I take the max over ZSA plus PSA over A, this will be bigger than this. Now what is this expression? This is exactly what you will get when you multiply Z plus P with this quantity, and the right hand side is what you will get when you multiply Z with this expression. So from this inequality one can then see that okay, this expression will be greater than equal to this expression, and hence this whole thing is greater than this expression minus this expression, and what we have over here is precisely the definition of f bar z, and hence one can conclude that your EI transpose f bar of z plus p is greater than equal to EI transpose f bar z. In other words, by making use of this relation, one can indeed show that your f bar has this quasi monotone increasing nature as desired, right. And because f bar also has this quasi monotone nature, right, one can now conclude that every solution trajectory of this ODE, right, and every solution trajectory of this ODE satisfy this relation whenever x0 is upper bounded by x bar 0. So let me elaborate. You take any solution of this ODE and let us call it as x of t, and let us take any solution of this and let us call it as x bar of t, and suppose x of t and x bar of t satisfy this initial condition relation where the strict inequality needs to hold coordinate wise, then one can show that this inequality carries over to x of t and x bar of t for every t bigger than equal to 0, right. And because x of t is upper bounded by x bar of t for every t bigger than equal to 0, one can conclude that the lim sup of x of t is upper bounded by the lim sup of x bar of t. However, we know that every solution trajectory of this ODE goes to the origin, hence this expression must be 0, from which, and using the fact that x of t is qt minus q star, one can conclude that lim sup of q of t is less than equal to q star. So let me just summarize what we have managed to do. On the one hand, we showed that every solution trajectory of this ODE goes to the origin, and every solution trajectory of this is upper bounded by a suitable solution trajectory of this, right, and from this we managed to conclude this, and hence one can make use of the fact that x of t is q of t minus q star, where q of t is the suitable solution trajectory of the limiting ODE associated with your q learning algorithm. One can use this to conclude that lim sup of q of t is less than equal to q star wherever the solution trajectory starts from, right. And using similar arguments, one can also show that lim inf of q of t is greater than equal to q star. You can look at the Dongwon, Lee and Hay paper to verify this, right. So what we have now managed to show is that for any solution trajectories of the limiting ODE associated with your q learning algorithm, lim inf of q of t and lim sup of q of t, which have this relation by default, right, will always be lower bounded by q star and upper bounded by q star, and then by invoking the sandwich property, one can show that for any solution trajectory of the limiting ODE of your q learning algorithms limiting ODE, right, the limit exists and the limit will be q star. right. In other words, for any solution trajectory, the limiting I mean the solution trajectory will have a limit, and that limit will be q star, from which we can conclude that q star is a globally asymptotically stable equilibrium of this ODE, right. And now by using your conditions from the stochastic approximation theory that we had studied, that is by verifying your assumptions A1, A2, A3 and A4, and some of which I have already proved, right. One can see that one can show that the limiting behavior that we have shown for the solution trajectories of the limiting ODE associated with the Q learning algorithm also carries over to the iterates of your Q learning algorithm, and one can then conclude that the limiting behavior of the Q learning algorithm will also be Q star, right. And in this way one can show that if you have this Q learning algorithm, right, which actually makes use of data obtained by interacting with the environment using this behavior policy mu, one can show that the limiting behavior will mirror that of the limiting behavior of your limiting ODE, and hence one can show that your Q learning algorithm will converge to Q star. And as I told you, once you get Q star, the optimal policy can be easily estimated, because the optimal policy is basically greedy with respect to Q star. So if you can somehow get a good enough estimate of Q star such that the ordering of the different state action values are matching those of your Q star's ordering, then from this estimate itself one can get an estimate of Q star, right. So of course the problem with this algorithm is that this algorithm is run in the in a space whose dimension equals the product of the state and action spaces, right. And when the state and action spaces are very large, then running this algorithm becomes problematic. So in summary, in the no function approximation case, the Q learning algorithm is good enough to find Q star. However, in practice the state and action spaces are very large and we cannot run this algorithm. So now the question becomes how we can run it in an approximate way. This will be the discussion in the forthcoming class. Until then, thank you and namaste.